Right. Okay. Well, look, I'd like to welcome you all. Um, my name's Richard Gateskill. I'm the director of the Center for the Fundamental Physics of the Universe, which is a center that's been set up here at Brown University. One of the areas that we've been, myself and many of my colleagues here at Brown, and also people who are associated with the center, has been looking at is that area of AI. We're using it a great deal within our respective areas of physics. And those areas of physics are, as you'll see from the modules that we have planned for those of you who are attending the workshops over the next 3 days, that the impact of these techniques is extremely effective. Now, this event is being organized by the Department of Physics as well here at Brown University, and I must, since there's not really going to be an opportunity for me to thank some of the people involved in this, I did want to thank Ariel Green up front, our center administrator, who's been doing a fantastic job of getting everything established for this. She is the point of contact. She'll love me for telling you this, but she is the point of contact. If you have any issues, you're able to reach her through the address as shown in Indigo, which we're using to sort of manage the overall workshop. And then I'd also like to thank Sean Dewey in particular, who's also been enormously helpful from a logistics point of view. Anyway, but thank you both of you for all the work you've been doing. And there are, as you'll see, there'll be many names attributed with the various modules that we're going to be giving. We're working on a sort of Eastern time slot, but I hope it'll be relatively convenient for many of you across the country and outside the US. But we will be, as you'll see from the Indigo, having morning session and afternoon session. Each module is designed to be self-contained. So if you miss a module, that shouldn't in any way create an issue for you understanding one of the other modules. The modules are presented in terms of a talk and then a workbook, full worked exercise. You will need to use Google. We are heavily dependent on Google, Google Colab and Google Drive for these things. So please do make sure, as described in Indigo, that you're able to follow that. So anyway, let me just introduce the sort of idea behind this panel discussion that we're going to have for the next hour. I think one of the things that is striking me is I hope all of you attending will be familiar with processes that are governed, should we say, by exponentials. Now, the obvious one is say the capability of computers. We could put it various different ways. The sort of floating point operation is one of them. But as some of you have seen in your lifetimes, we've moved from tera 10 to the 12 to peta 10 to the 15, and we're now entering the exa 10 to the 18 exaflop era. Each one of those SI prefixes hides within it 3 orders of magnitude. And the fact that we're taking a similar amount of time, of the order of sort of say 12, 14 years to do 3 orders of magnitude to move through each of those titles is classically, characteristic of an exponential or geometric, process. And, so much so that what was considered to be a supercomputer in '96, by the time you're barely 15 years later, you had the same processing in a fairly mediocre telephone in your hand, which is remarkable. But I think as scientists, you will be familiar with this idea that you just simply use log, you use log axes in order to best deal with exponential or geometric processes. But of course, at a practical level, and this is where the sort of segue into AI, it is very clear that AI capability is itself extending on average in a way that is exponential. But of course, where it directly interfaces us as humans, it's quite difficult, or can be, to to cope with just that ever apparently accelerating rate at which it does. Having said that, it is, I think, one doesn't want to take a that closed attitude towards what I think as scientists, I would hope all of you are able to, sort of embrace these new capabilities that are going to be there, and in fact, you look forward to and enjoy these opportunities, these new opportunities that it's going to provide all of you to, to conduct your work. And I think, nobody, well, we are, of course, this panel is attempting to hold up a crystal ball, but on the other hand, we're all willing to be sort of surprised by what is likely to happen in the future, but I think you all want to be embracing that future, and to that end, this is our sort of motivation for holding this workshop or in these series, is an on-ramp. We are trying to give as many of you as possible examples of readily understandable problems in various diverse areas of science that then allow you to see how it can be applied, do so in a way that you take away and go ahead and imply it. So I think that this discussion today, just to start warming up on it, I'll just briefly summarize the idea behind the discussion, and then I must also thank and introduce and thank our panelists. So in terms of where we're trying to go with this panel, the growth and capabilities of AI systems is as I've already tried to motivate, is clearly showing every sign of improving exponentially, although I think it's also fair to say that it's been somewhat unevenly distributed in the places where we've seen the biggest changes. Some areas are lagging, but I think we're also all prepared to sort of understand that an area that's lagging today is likely to go through some kind of jump, unexpected jump, subsequently. And we're seeing already remarkable new discoveries in a couple of different ways. The data discovery side is making it possible to sift through large amounts of new experimental data. I mean, we're seeing this very directly in materials science, biochemistry, particle physics, astrophysics areas closer to my area, and we're finding that new patterns that would probably certainly would have taken a lot longer to establish without these techniques. And then I think it's also fair, another area is on the theoretical side, where it's allowing modeling, to narrow down the physical configurations, say in quantum systems or in protein folding, as very good examples. And we are not only interested to see how things will continue in those existing areas, but I think critically what other new areas are going to benefit. And then I think the other, another question is clearly that, when will AI systems be able to come up with their own questions and physics models, scientific models beyond what humans have already envisaged, which is a huge question, a huge issue. We are really at early stage, but nonetheless, I think it's something. We do learn from discussions of this, and I think maybe we'll get a chance to touch on some of those areas, as challenging as they are to discuss right now. Are we going to see AI undergo the sort of intellectual inspiration that is so critical to the scientific process, or how are humans going to benefit from those kind of inspirations? So to that end, we are extremely grateful, extremely lucky to have a number of researchers who are working and are thinking the leading edge in their research, and they, I think, have demonstrated that they are also very keen to understand how AI is going to impact them. So Sean Carroll is here with us from Johns Hopkins. Thank you very much for joining. Sean is absolutely prodigious, and we're grateful for it, because he I think in terms of outreach and helping people understand some of the more complexities of many areas of physics, including my own in cosmology and particles, has been showing thing. I think that if you go to I don't know, preposterous universe. I should have rehearsed that one. Preposterousuniverse.com. Sean does cover a number of the areas where where Sean is most productive, and of course he also has written a number of conventional books as well, including Space-Time and Geometry, Particles, End of the Universe, The Big Picture on Origins of Life, Meaning, and the Universe Itself, which fantastic. Thank you. So I must move forward. Jesse Thaler from MIT is here. Jesse is also, is particle physicist at MIT. He's the inaugural director of the NSF Institute for Artificial Intelligence and Fundamental Interactions, which is very much focused on direct exploitation and development of new ideas in AI that impact a range of physics. And it's one of the things that I saw many or some of you out there have seen is that the funding agencies have understood just how critical funding and making resources available to researchers to look at this. And Jesse has been at the forefront of this aggressive development, which is fantastic. Then David Shi from Rutgers is also here, and again, thank you so much. David is a theoretical physicist, and he's been very directly looking at applications of machine learning and AI, and is doing so in both colliders and astronomy, which is it's been fascinating to see some of the insights that are already coming from this work and that will continue to exponentially grow. Thank you. And then lastly, Ilya Nikolov, who is from Brown here, our institution. He works in the condensed matter NMR group here with one of our other colleagues, who's now chair, actually, Professor Mitrovic. And again, they've been receiving a number of funding directly supporting sort of quantum initiative and the AI design probes that are being used to to monitor quantum phase in magnetic resonance experiments. And as you'll see from a number of the different modules that we've tried to form for this workshop over the next 3 days, we are drawing from condensed matter and from particle physics and astronomy, trying across the board, just to really give all of you attending the various aspects of the workshop a chance to see AR being applied in as many areas as possible. So let me, at this point, I'm going to stop talking and just simply pose a question or two, or sorry, one question to just get our panel warmed up. So I think, although we'd like to in a little while talk about looking forward, I think it always helps to sort of ask ourselves the question: how has AI impacted us to date? Are there particular areas or anecdotally an observation or one or two observations that characterize how it's been enabled to impact us now? And I think why don't I start this time going through in the order I just introduced everybody. So possibly Sean, let's start with you, and then we'll move to Jesse, David, and then Ilya. Thank you.
Sure. I think I can actually be pretty quick because I suspect that AI has impacted my research and working life less than the other panelists. I'm a theorist, but still very much a pencil and paper kind of theorist. So I would say that AI, by which we mean modern large language model kinds of things, has impacted my research in 2 ways. Number one, as kind of a super Wikipedia. I can look things up, and just like Wikipedia, I don't trust what it tells me, but I can, then go verify it somewhere else. And even something as trivial as, what is the notation that is most commonly used for something? I can just find it right away in a way that was hard before. And the other is that, some of my research is actually simple numerical modeling of things, and it's becoming more of that in recent years. And and I haven't been an active coder since I was an undergraduate or maybe graduate school. So I'm very, very happy that now I have a little AI assistant that can help me write simple programs, that can help me do research. So these are both conveniences for me, but they're not profound. They're not changing the way I'm doing things. I think that AI, as we know it right now, the future is hard to predict, but something like come up with a new conceptualization of how space-time emerges from quantum gravity, those kinds of questions AI is not very good at right now.
Thank you. Jesse.
Well, so I'm glad that Sean started off with something provocative and saying by AI we mean generative modeling, large language modeling, because where I would start actually for me is back in 2016. And in 2016, this is before LLMs. This is when we were seeing kind of the emergence of deep learning architectures, particularly for image processing, starting to come into my field of particle physics. I am on the record in 2016 about talking about all my friends who were doing this deep learning and me saying, look, I was trained as a theoretical physicist, and what I believe we should be doing instead is doing deep thinking. And that's what I said. And I basically was completely dismissive of that whole area. So much so, when I had these two spectacular graduate students, Patrick Kamitsky and Eric Metodiev, they came into my office at MIT saying, hey, look at what we've done with image processing and how we can use image processing to understand certain properties of the strong nuclear force. I said, no way, your paper is total crap. Get out of my office. And it took a while, but eventually they returned and started step by step trying to convince me that actually machine learning, deep learning was actually a way to solve our problems. And in particular, on this blackboard behind me at MIT, I basically wrote, look, if you can solve these equations using deep learning, then I'm sold. But there's no possible way that you can solve this with deep learning. This is an impossible problem to solve. And they came back and they said, oh, by the way, you realize that there's actually a paper in the machine learning literature from last year that has those exact same equations, and here's the solution. And I was blown away. And that's when it really did have a profound change in my research, even from a technical perspective, that what am I doing now is instead of saying, let me go and think about it as AI as some kind of intelligent creature, let me think about it as a rigorous mathematical framing. And if I can convert my problems in theoretical physics into a rigorous computational or statistical problem, then it's likely that someone in the machine learning literature will have a solution to it. And indeed, that was the motivation for starting this institute, the Institute for Artificial Intelligence and Fundamental Interactions, is to find those connections and really thinking about AI, again, in this rigorous mathematical statistics, almost theoretical computer science language. And now I find myself in the skeptical shoes of now these large language models are coming out. People are showing all this great work with it. And I am now once again in curmudgeon mode, saying, okay, but tell me what's the rigorous thing behind it. And now I'm just waiting for the next graduate students to come to my door and actually convince me that the tools that will help us, code or, help us be, kind of a Wikipedia on steroids actually can enable us to do scientific discovery. So looking forward to this panel to see what thoughts others have about, that kind of exponential growth, especially in kind of the language there.
Thank you. David.
So yeah, I think I would also, so Jesse said many of the things I was going to say. I'm also a theorist. Actually, I come from an even more theoretical background, I guess. So I started out as a string theorist in my PhD days, and I've gradually been coming down in energy or length scale. And so here I am today, pretty much doing machine learning applications to physics and astronomy full time. So it's gone from also being very skeptical, and for me also it started with a student, Sebastian, who came into my office one day and said, I'm thinking about leaving the field, but I don't want to go to finance, so I'm looking for something more meaningful to do with my life. And there's this thing, machine learning, that seems very interesting, so I want to learn more about that. I was also very skeptical of the whole thing, and like, this is not physics, grumble, grumble. But yeah, since then I've also majorly drank the Kool-Aid to the point where it's sort of taken over my research program. And to me, it seems also like a paradigm shift in how we think about data and how we think about how data and physics go together. And the kind of work that we're doing, it's almost like the machine learning tools are giving us a new kind of telescope to look into, not into the sky or into the microscopic realm, but into data. It's letting us see further and deeper into the data than we ever could before. And that is, to me, very exciting. And just like the inventors of the telescope or the microscope, we now have access to these really powerful tools, and we can see things and go places where people have never gone before. So it's a very exciting time. And having worked on some very mature fields in the past, like string theory and supersymmetry, this is probably my first experience, for the last 5 years or so, in a completely immature field, and it's really fun. So for the students in the audience, I highly encourage you to try to get your advisors into this thing if they're not already, and also you can really go out there and just be extremely creative in ways. So it's really nice to be first. This is still a very young area where there's so many neat things to try, where you can really be first. So yeah, lots of low-hanging fruit. So I highly encourage people to, take that away from this event if you could. Yeah.
Thank you. Ilya.
Hi everyone. I think I'm in the minority here because I'm an experimentalist. Although my experimentalist friends would disagree, they would say that I'm also a theorist. And I'm saying that because we have implemented a lot of machine learning into our research. And basically, thanks to some simulations that we've done, and thanks to the big data that I've generated, theoretically, we were able to create a new method of looking into our NMR spectra, because we're working with magnetic resonance. We're looking at the nuclear spins, but we're trying to study the structure of materials and how the electrons are aligned and the phases they undergo. And they can be very complicated. And luckily, I convinced, or my advisor was already convinced also, to try out machine learning to look at all the data. And now we're very happy because we found a new way to look at the spectra and understand some phases that are very complicated and solve some problems that were hanging out in the literature since a while ago. So yeah, it's very exciting that also not only theory, but also experimental physics can get inspired by machine learning. Yeah.
Thank you. Thank you. So I should mention, actually, I didn't want to mention it too early, but I do feel like maybe I should mention it now. We do have a Q&A channel open in the Zoom. It's just for typed questions. If we have a chance near the end of the panel, if you want to shape a question, don't feel you have to ask it immediately. We'll only probably get to one or two. It'll be a bit of a random stochastic anyway. And I do urge you to pay attention to to what the panelists are saying. So don't spend the entire rest of the time just thinking up your question. But please, if you do want to ask the panelists a question, I know I do, but I'm lucky because I'm able to actually ask them. But I'm more than happy to act as a conduit through the text-based interface to ask a question of the panelists. So I think now at this point I'm just going to throw some ideas out and just we'll see sort of randomly which panelists feel most comfortable with it. But for me, this is, and I know maybe this is whiplash time, but one or two of you have hinted at this already, that we're obviously seeing huge progress on the word soup, the word salad, LLM side, but it's a little bit of a jungle out there. We're not seeing some of the sort of discipline that necessarily scientists we're used to seeing in terms of the way different bits of information are interrelated to one another. I think we're all asking ourselves this question: how long is it going to take, and are we going to see LLMs that are chaperoned or guided or forced to obey, more logic, and therefore maybe be a system that we can engage with more that is less based on probabilistic associations of words or phrases, and more, should we say, driven by a logical consistency. I don't do with the work those of you are doing. Are you seeing evidence of that yet coming into the tools that you've either been able to use firsthand, or ones that you've come across or heard of people talking about? Is there any prospect short-ish next year or two for this kind of more logically rigorous tool to appear? Please, if one of you would like to, Sean, please.
I could say something. Yeah, I think that, to me, it's fascinating how people react to the undoubted success of LLMs at a certain kind of thing. The philosopher Daniel Dennett talks about what he calls the intentional stance. We, from our evolution, from our education, from our socialization, cannot help but conceptualize certain things as agents with cognition. We even talk about toasters and cars as being in a bad mood or whatever. So when we're faced with something like an LLM that can talk in this clearly very human way, we instantly tend to think that it's doing human-like thinking, and they're fundamentally not. And I think that we're really having trouble accepting both that they're much better than human beings at some things and much worse at other things, and clearly delineating what those are. Like, if you wanted to, I don't know, if you wanted to ask ChatGPT to write a series of limericks in the style of Hunter S. Thompson that explains the second law of thermodynamics, it would be much better than a human being could do on a much shorter time scale. But that's because it sort of has the words there, and it's looking up things next, and it is very good at that. But just on the other day, people were making fun of it because on Twitter, on what used to be called Twitter, they started asking it, name a famous philosopher whose name begins with the letter M. And it said Aristotle over and over again. And so it's not that it makes mistakes. Making mistakes is fine, but the kind of mistakes that it makes is very illuminating. And to get to the answer, the actual point here, I think that there's a certain type of task for which LLMs or deep learning more generally is going to be super duper useful. And exactly this kind of data analysis, equation solving is exactly what I think it will accelerate in very obvious ways. The more conceptual things, the more, LLMs can be Tycho and Kepler. It will be harder for them to be Newton and Galileo in a certain way. It would be very hard for them to be Einstein or Niels Bohr. That's not to say that AI can't do that. As Jesse completely correctly says, there's different versions of AI, and we're all machines at some end of the day kind of sense. But the specific things that they've gotten very good at right now are much better at interpolation than extrapolation. And so I think that it's going to be a revolution in certain areas, not in others. And we got to get better at figuring out what those areas are.
Yes, please.
Sorry.
David, yes, please.
Yeah, maybe I'll just add a bit to that. So my understanding, so first of all, I think, where the LLMs are going, it's impossible to predict. There's like 10,000 papers at NeurIPS every year, and maybe half of them are about LLMs these days. So there's a huge amount of R&D going into that, and I'm certainly not following all of that closely. But my impression is the current paradigm is one where they're trying to basically learn the probability density of, say, words in a sequence. So they're trying to learn things probabilistically. And so it's like a generative process where they generate more words from some probability density conditioned on the previous words. And so in my experience, that kind of approach generally is very good at learning approximations to your data, which are kind of naturally broadened because they can't be perfect delta functions. So what you're learning is something fuzzy. And when it makes some egregious mistake in this very high dimensional space, I think that we would consider sort of an obvious silly mistake, one of factual error. I think what we're seeing there is this fuzziness. And so it's very hard to get these probabilistic generative models to learn delta functions. And so when you're faced with a factual question where there's sort of one true answer or a discrete set of true answers, it's basically can't localize itself onto this delta function like submanifold. So I think that's a lot of what's going on, and there's probably hundreds of papers of people trying to improve on that in various ways. And I think I wouldn't be surprised if there are breakthroughs coming, or they're already out there, just not aware of them. So yeah. But I think that's the part of the problem with it not being able to reason or answer factually right now. Yeah.
Jesse, I think you.
Yeah. So I really like something that Dave said earlier about kind of machine learning, deep learning as being kind of a microscope on data and giving us new ways of interacting with data. And if I allow myself to be really optimistic, and despite the challenges of LLMs, or despite hallucinations or other concerns, for example, the failure to cite references, at least in current generation language models, but think about whether it could ever be a kind of microscope on concepts, and whether you could actually take concepts and disentangle them, something that we usually associate with language. That would be quite interesting. And the point that's raised about it being probabilistic and that kind of has a fuzziness to it, there is a part of me that wonders whether or not actually scientific reasoning, coming up with what we usually ascribe to great leaps of intuition, actually has a fuzzified version of it. If we think about something like general relativity and think about the pathway that got you to general relativity as defined by the way that the human approached the problem, and then kind of step back and ask, is there a fuzziness, probabilistic, steepest gradient descent in some kind of landscape of theory space? Is there an alternate way of posing that possibility of discovery? That may be a strategy for coming up with new concepts, or strategy for scrutinizing concepts that may be actually more suited for machine type logic or fuzzy logic, or more probabilistic reasoning. And so I guess sometimes I like to kind of flip it on its head, and instead of asking the question, can a machine think like a human and come up with the kind of conceptual leaps that a human could, or synthesize information the way a human could, actually flip it around and ask, are we sure that in this time where we are right now, is it possible that we need to go the other direction, and that actually we as humans need to think a little bit more like the computer and actually phrase what we're trying to do in a more computational language, such that you could do exhaustive search, such that you could do symbolic regression, such that you could do some kind of concept fuzzification, mishmashing in order to come up with new ideas. And it a little bit hinges on whether you think some of the pinnacles of modern physics, whether they are like isolated delta function points that, again, it would be very difficult for a machine to find, or whether there's some kind of gradient descent that might get you closer and closer and closer to a deeper truth. And the skeptical part of me really thinks that no, actually these concepts are delta functions and therefore basically impossible to identify. But there is this part of me that wonders, am I missing something? And is there a fuzzification of our laws of physics that might allow us to kind of gradient descent to better answers?
Thank you. Very good. Does anybody want to expand on or extend on that point? Okay, no, otherwise let's so and you were touching on this, I think, so this makes it a good point to ask this question. There is, if you like, a difference in approach when you're working with machine learning AI algorithms, in that it was necessary in the more traditional scientific method for us, especially within physics, but I think this is true of many scientific disciplines, this atomistic taking apart of systems. I know I'm being way too general here, but it is fair to say that the way in with ML techniques is often by getting hold of enough data to sort of define the boundary conditions, or some of the individual sort of anchor points, within it, and then of course have the have the algorithm actually dig in and see the best way or the most efficient way or the effective way to connect those points. Is there any, do you either you might have comment on that in terms of this being a new, is this a profoundly new way of hitting problems, but also are there any dangers associated with it? I mean, one most obvious danger that people often talk about is this black box. And there is this sort of side channel, which is from the more from a human intellectual point of view, if we start accepting the idea that it's okay to have black boxes peppered in amongst our ladders, our Wittgensteinian whatever, our ladders of thought, is this going to leave us vulnerable or somehow? But that's sorry, that's a sidebar. If somebody wants to pick up on, they can. But I think more do you see problems with that flip in giving up on the atomistic way of trying to form new scientific ideas? Is that a problem for us in science, or is it, or actually do we need to be do we need the shake up? Do we need to find ourselves trying to solve problems in this? Please, David.
So let me just make a few comments that your question sparks some thoughts on. I mean, I'm not sure it's answering exactly what you're asking, but one thing I do see, the current excitement about ML and current sort of breakthroughs we're seeing, and fascinating progress we're seeing in ML and AI as applied to science, is possibly like a paradigm shift or kind of a new category of like physicists that's emerging. And it's something I know several of us have thought a lot about and talked about, sort of a structural thing in our field even. So we're used to having the idea of a theorist and an experimentalist. The experimentalist, makes the experiment, collects the data, at least in particle physics, analyzes the data, doesn't let us even see the data, and then shows us the results, and then the theorist takes those and thinks about them very hard and translates them into models and comes back with predictions or limits on other models, and then the cycle continues. But with the growth of machine learning and data science and how it's impinging on our field, I think we're maybe seeing a third category of physicists emerge, like a data physicist. And this is somebody whose skill set is different than the traditional theorist or the traditional experimentalist, and very much informed by statistics and data science and computer science. And yeah, that's the goal of the data physicists or data scientists working in physics, would be to get insights in a data-driven way, ideally, or putting models together with the interfacing models with the data and learning something from that. And then talking to the experimentalist to improve the experiment or collect different kinds of data, or talking to the theorist to build better models, et cetera, et cetera. So there's a data analysis component here that's sort of growing, I think, in complexity and richness. So that's one thing I see, which maybe relates to what you were saying, I think.
Yeah.
Yeah, let me riff on that and just say something completely heretical. At MIT, every first-year student has to take 2 semesters of physics. And those 2 semesters of physics are grounded in calculus. And calculus, deterministic processes, kind of similar to the atomistic things that Rick, we were talking about, like that is the entry point that we have to the physical world. And the rise of the data physicist, the rise of ML, or for people who already know about this and for finite temperature systems, kind of statistical foundations. What if instead of students coming in to MIT with calculus as the thing that they live and breathe, what if they came in with statistics as the thing that they live and breathe, the probability and statistics? That seems to be the direction that at least the kind of the deluge of data is going in, and maybe even decision making in society overall, understanding probability and statistics may actually be more important for people than understanding calculus. But that would be a kind of a complete change in where you start off with, and then it would be saying, yes, what you're given are piles of data, some of which can be trusted, some of which can't be trusted. You have to think about how you reason with that data. And it's a very different type of reasoning skill than you have with the more calculus-based analytic logical structures that certainly I was trained to do. And so that's something to think about, is thinking about, even going to high school levels, is there a different mode of thinking that we need in this century, if it's the century of AI, and does that actually open up interesting opportunities for rethinking the way that we conceptualize physical systems?
And I'll just add one more thing. Sorry. So, I think there are maybe eras in scientific history where top down is the way to go. Like the theorists are in control. They've got the models. We just got to look for them. And there's eras where like really bottom up, like building a tabletop experiment is the way to go. And then I don't know if this era that we're in now has ever happened before, but we're in like some kind of data rich era where we don't know what the models are. We're not even sure maybe what experiment to build, but we have a lot of data. So, and there's got to be some, insights in there that if we just look hard enough, we could find, and that would inform, eventually we'd find ourselves in a more traditional mode again. But I do feel like we're in a different sort of time, like having worked on a lot of these top-down models in the past, and, none of them have turned up at the LHC. We really don't know what we're looking for, I think, at this stage. And I for one, I think a lot of us are more and more willing to just sort of listen to the data and see what it has to say, without imposing, some preconceived top-down ideas on it. So yeah, I think that's another thing I would add to what Jesse just said. Yeah.
Are we suggesting that that approach is because that is much more human, or is it just that we've been trained? That is the scientific method in which we've been trained, and therefore we are able to be retrained and working maybe in the future, working with AI tools, these machine learning data analysis techniques that will allow us to to retrain our human minds, or are instead is the suggestion that actually this is where our rather humble intellects are no longer suitable for solving these problems, and that actually we will have to design and machine learning that is able to make more progress. Are we part of the equation, or are we gonna move aside and be observers of the successes that the machine learning is going to make in some of the scientific areas?
Well, go on, Ilya.
I was just gonna say that I feel like we as scientists, and I've been trained also as a scientist, as a physicist, that we're looking for some ideals of beauty. And when I go in theory, and the theory is very beautiful, in NMR you see these beautiful peaks, but when we go and measure in the experiments, the data is much more messy. And I feel like as we go forward, we're going to look more on this messiness and trying to understand where it comes from. And I think basically this is where AI and machine learning is going to come and help us, because I think so far we've been trained to look at some beautiful things because theory gives us beautiful things. But I think AI doesn't care about this concept of beauty, and it just looks at the data, it tries to interpret it. So, and I think that's why we've been, in the past, I think that's why when we say what's been influencing the most, I think in physics it's been this ideal of beauty, and trying to make sure that the data looks nice. But when I go in the lab, the data doesn't look that nice.
So we've been hindered a little bit by our obsession with beauty. Jesse, sorry, you were.
Unfortunately or fortunately, depending on your perspective, what science is at some level is what scientists do. And if the AI has some kind of insight or revelation, but it can't communicate it in a way that a human can interpret, then unfortunately, that won't be something that, for example, a Nobel Prize committee would be able to understand or appreciate. So you pose this as a kind of dichotomy. Do we need to change our training, and maybe we'll be able to kind of think in this new way, or will the AI supplant us? It probably these things are a little bit more conjoined, in the sense that I don't think you're going to be able to have scientific reasoning without some of the standard things that we do in science, like uncertainty quantification and understanding systematics. Like those things are going to persist. And so we're going to have to figure out how do we navigate that. And part of that may indeed involve a change in our training. And that should be something that's exciting to us. Now, what's a fascinating question, which Dave was raising, is, are we in this new era? Because clearly the previous era, we did incredibly well with calculus-based reasoning. It was fantastic. I mean, just the foundation of my work with quantum field theory is incredible. And that's a triumph of human ingenuity. There's kind of two questions you can ask. One is you can say, are we in a different era? Or another one could be, could you imagine a different scientific history of which you would get to similar realizations that we've already had? For example, the establishment of the standard model of particle physics. Could you have gotten that through a different lens? And that's something that we, of course, we don't know, but that's part of the dialogue that's going on right now. Was there something unique about the previous method, and now we're doing something different? Or actually, what we're doing now could have been also been done in the past, or what we had done in the past, could that actually be relevant for the future if only we were a little bit smarter?
I'll just say something very quickly, which probably everyone will agree with, but we got to keep in mind that the purpose for human beings doing science is understanding things. And that sounds pretty straightforward, but there is like a little positivist strain in modern scientists sometimes. If you know the introduction to Steven Weinberg's classic textbook, Gravitation and Cosmology, he says, why do people keep talking about all this geometry of space-time stuff? All I care about is predicting the locations of dots on photographic plates. That was not right. He was not, even Jove nods sometimes. That was a rare misstep from Steven Weinberg, because we do care about the understanding of it. If someone gave you a black box and said, you can ask this black box any question about, a physical setup and ask what will happen, and the box will tell you what will happen and it will be correct, would that count as a successful scientific theory, the existence of the box? No, because we don't understand what was going on there. And so I think two things. One is that AI might very well be helpful in getting us there in the understanding, but part of the challenge there is understanding what's going on inside the AI. This is a very fun, cutting-edge research area within machine learning, et cetera, is making it more transparent. Okay, how is it that these deep learning networks are able to do these things? We're not even very good at that. So I think that near term, maybe not far term, but near term, the human beings are absolutely inextricable from the equation.
Yeah, I also view it as I'm wary of making predictions when something is growing exponentially. So whether or not we'll be replaced by an AI physicist, who knows? But yeah, it doesn't seem like it's going to happen immediately. Plus, ultimately, we're doing science for ourselves, so we want to understand, I think, as humans. But yeah, to me, it seems like a growing collection of increasingly powerful tools, and it's up to us to learn how to use them and deploy them and get the most out of our data, and responsibly, with uncertainties and all that. So it's a new kind of toolbox, and I think that that goes in the direction of like retraining ourselves to learn a new bag of tricks. And it's sort of, instead of calculus, it's statistics, et cetera, et cetera. So it's a fascinating set of new instruments, I think.
Yes. No, I have some questions that were asked by members of the audience. I feel that I should, before we run out of time, make sure I address one or two of them. Let's see. So actually, I will say this is an area of research I'm not familiar with, but it may, one or more of you on the panel may. It's referring to recent work done by Halvorsen and others concerning quantum field theories with neural nets. I don't know whether anybody, and in particular, they've been using QFT neural net links in glassy systems and other statistical mechanical systems, to try to understand modeling through neural nets. Is that something you're familiar with or would like to comment on? Or one of the, I think I see Jesse might, yeah, please.
Yes. So Jim Halverson from Northeastern University, he's one of my colleagues in IFI. So of course I have to advertise how wonderful his work is. But one thing that's quite fascinating, and this is showing up in more than just Jim's work, but there's kind of a community of people who are realizing that AI systems just as systems themselves, as complex interacting systems, they have interesting analogs in the physical world. Yep. And so neural networks happen to have interesting analogs with condensed matter systems, with field theories. And it turns out that some of the optimization strategies that are used in training machine learning actually has interesting connections to just classical mechanics. And so physicists actually, in some sense, are ideally positioned to understand some of the interesting dynamics that are emergent out of machine learning systems. If you think about machine learning as just a complex interacting a system, whether it's classical or quantum, that toolbox of trying to understand then what its behavior might be and make predictions about how a machine might operate, that is something that physicists actually are quite uniquely positioned on. And within our institute, it tends to be people who have this background in, let's say, quantum many body physics. They are realizing that some of the techniques that they've developed to understand physical systems that you can build in the lab, those same techniques are relevant for understanding how the machine learns, how it generalizes, and things like that. So statistics not only shows up in the way that we're interpreting data, but also it shows up in the way that the machine itself is doing its interpretation. And again, that's a fascinating application of physics for understanding of machine learning.
Yes, and as Sean and David and yourself were all suggesting, that highly necessary if we are to actually understand what's going on under the hood as well, in terms of some of these new AI systems. We need to look further.
I'll just share one little anecdote there. It was bugging me for like several years even. People were referring to a lot of these neural network models as non-parametric. And it was really bothering me because to me, it seemed like they're the opposite of non-parametric. They're many, many parametric. They have, millions or billions of parameters. How can you call them non-parametric? And it turns out that at least some of them, maybe what they meant is that you get to the level of so many parameters that actually some collective emergent phenomena, some like normal modes or something, emerge in some ill-defined way in the parameter space of these models. And so it's more useful to think of them as sort of a continuous parametric or non-parametric in that sense. And that's what people are seeing, at least with some exactly solvable limits of these models. Some simple, they're reducing to some simple collective, like free field theories or something. So yeah, there's a lot of actually literature on that, which yeah, be happy to recommend more of.
So another theme that's clear in a couple of questions we've been asked, I think people are interested, we touched on earlier, I think Jesse, you introduced it first, but I think Sean was there as well. The fact that having been so conspicuously unsuccessful or unlucky, maybe it's better to say unlucky in terms of the explanations for particle physics top-down models that we expected to see evidence of, and that maybe we need to become more of a just straight believer in data, and that the theory will somehow come out of that. Specifically on this area, do we have the right machine learning tools to sort of meet a challenge like that, or are we going to need a significant steps forward in terms of the ML architectures, the AI architectures themselves, to allow us, for instance, to give us a core in particle physics, say, where we have this issue of a lot of data, but not yet a theory that is highly motivated by that. We're testing theories, but is that maybe there's a different mode, as was being suggested earlier, that somehow a theory comes together from the data that wasn't simply top down and then tested?
So let me give you an example of something that in principle we could do. but we don't have the computational resources to implement. So let's say you're 100% convinced that physics at, let's say, the Large Hadron Collider is described by an effective field theory. You could figure out a parameterization of all possible effective field theories with all possible field content, subject to the rules that we already have, or even you allow yourself small deformations of those rules. And then you could, in principle, compute the implications of each of those field theories and compare to the data and then make inference about which field theory was the right one. Now, why don't we do that? So one gets at what Sean was saying is like, we'd like to have some understanding. And so if you just kind of randomly throw field content in there, there's a sense of what are you really doing? What are you really trying to explain? Also, the data itself is not fully constraining. There's something like Occam's razor that we usually invoke to try to find simpler explanations. There may be a lot of different field theories that are consistent with the data just because the data is not very constraining. But then just from a computational perspective, we think that even just given one field theory, calculating the implications of that field theory is extremely computationally expensive, let alone trying to do backpropagation through that to try to gradient descent in the landscape of all possible field theories. And so there is something that bugs me, irks me, or makes me concerned. We're talking about the exponential growth of computing, but some problems we think are just really hard. And of course, we can argue about P versus NP and what classes various scientific problems might appear in. But we just think that certain things take a large amount of computational resources, and whatever shortcuts that AI is allowing us to do, we'd be a little bit surprised if it were able to solve what we conceive of as being very, very hard problems. And so that's when I'm kind of cynical about the direction when people say AI is going to do this, that, and the other. It's like, well, we think that certain problems are just computationally very hard, and that even with exponential resources, it might be extremely difficult to find answers to. And that's the question: is the time we're in, or the data that we're confronted with, is it just so computationally challenging that even with this exponential growth, we still may not be able to do kind of AI-guided strategies that we liked for the purpose of discovery?
Yes. Yes.
I think, yeah, just to add to that, yeah, like for instance, the growth of Feynman diagrams is faster than exponential, right? So I think just exponential growth isn't going to let us calculate perturbative QCD to as many orders as we might need, not to mention the non-perturbative part. But also, yeah, so I think many of us, especially at the LHC and also beyond, are very interested in like an alternative strategy, which is more data-driven. So instead of building a model, getting its prediction, and then comparing it to the data, it is possible actually to do model-agnostic searches, so data-driven searches. So one of the traditional ways to do that, which is sort of semi-model agnostic that everyone knows about, is the bump hunt, where you assume something little about your data, that it's smooth in the background and that your signal is localized somewhere. And then just leveraging that assumption, you can then look for many different possible signals, and without modeling the background in any detailed way. And that's proven to be hugely successful. We discovered the Higgs that way, and before that, the Z boson. So it's had and many other things. So it's had a great track record. And many of us are working on ways to enhance these bump hunts to look in a higher dimensional space. So I think there are ways to do data-driven, model-independent or semi-model independent searches. And then after you get the result, then you'll have sort of a subsample of the data, which you believe is signal-like. And then it's up to the human to dig into that and hopefully unpack what the patterns are, what's making this signal tick, and that's where I would see the handoff to the theorist or to the more traditional methods happening. But yeah, there are ways I think to get something useful out of the big data set in a more ML-driven way, I think.
So I think this is going to have to be the last question, but so we focused a lot on the sort of data-driven aspect, but do you look forward to an era where, if you like, a machine learning, AI model somehow becomes a muse? Somebody hinted at, actually, Sean, I think you were talking about how it's certainly alleviated. You can get information off Wikipedia style and what have you. But let's imagine a chunk, some more of a train of thought becomes rather than just individual facts, and that possibly machine learning becomes people talk about, especially I think humanities, but I'm sure in science as well, that a muse, somebody, either a colleague or or some other kind of spur to thinking. Do any of you look forward to an era where AI becomes your intellectual muse and brings helps you develop ideas, should we say, more rapidly, or indeed where no idea existed, helps you bring an idea into into existence? Is this something you've pondered on at all? Sean, please.
Yeah, I think this is once again a place where it's really crucially important to distinguish between kind of where the successes are right now with LLMs and deep learning versus where AI might go at some point. Yes, it's absolutely possible that you can use AI as a muse to inspire your own human creativity. I have a friend who uses the I Ching all the time to make difficult decisions, not because he thinks it's in touch with some mystical force out there in the universe, but you roll some random numbers, you figure out what it's telling you, and then you can reflect in a different way on whether or not that's really what you want to do or not. And that's the kind of way you could absolutely imagine using AI. I did when ChatGPT came out. I thought I would try to use it to solve some long-standing puzzles in philosophy, right? Give it a conundrum, the Sleeping Beauty problem or something like that, see what it comes out with. But as I should have known, of course, all it does is tell you what all the human beings have already said about this problem, because that's what it is trained to do. I think that you're going to have to get truly new insights. You're going to have a different kind of cognitive architecture than we currently have in large language models. I tend to think I would love to see this tested because it's just kind of an intuition. I could imagine current kinds of AI coming up with the Schrodinger equation. I can't really imagine them coming up with the Born rule or the probability interpretation, right? That was something like just brand new in a way of thinking about things. I'm absolutely willing to think that someday computers can think that way, but it's not what they're optimized for right now. So that's full employment for the new generation of young coders out there.
His colleagues, Jesse.
So one of the things that became very clear to me based on an April Fool's joke is that these large language models, the people who make them, they're making design decisions about how they want it to respond. And so the April Fool's joke was Siddharth Mishra Sharma, who's one of our I5 fellows, along with a team, built a virtual version of me, where they basically fine-tuned ChatGPT to respond as Jesse Thaler, director of the Institute for Artificial Intelligence and Fundamental Interactions. And so they were making a design decision. They were making a design decision on the tone that it was going to use. They were going to make a design decision that no matter what, it will always, say its name. It will always talk about particle physics. It will, always enthuse about machine learning. And that realization that with relatively little coding, it could behave in a very different way than the stock LLM. And so then, this makes me think, if the road to scientific insight is for us to be surprised, having that muse that can kind of push us to the edge, somehow finding that edge between completely insane ideas, versus things that are too conventional, what's on that boundary that might actually, inspire us. You can imagine someone making that as a design decision to build an agent that could make, Sean happy, or at least, have Sean, scratch his head and ponder things. And I guess I've been surprised by the flexibility of those tools to behave in ways that are again, surprising to me. And that is something that's maybe worthwhile exploring instead of just like this one style of intelligence, thinking about it as actually being itself a probabilistic distribution over probabilistic generators, and really selecting the one that might be best suited for whatever scientific need we might have at that point.
Colleagues, David, you anything to add? Otherwise, we've shot our time. It's so easy with these virtual ones to go over, but we shouldn't. We have other things to do. But just a reminder to everybody, 10 a.m. tomorrow. We adjusted the time, Eastern time, just to give those of you on the West Coast at least not total whiplash in terms of attending. But and I hope those of you in Europe, obviously the afternoon session will also start early enough. It's not too bad for you. But right now, what I should do is thank our panelists. Sean, Jesse, David, Ilya. It's been enormously. It's been fascinating listening to what you have to say. I know. Of course. Maybe this is how every generation feels, but I feel like one's leaving a hell of a mess for the next generation to deal with. But as I tried to get at the beginning, I hope most of you, as scientists, we tend to look at all the options and tend to sometimes over focus on the ones that could really go wrong. But I think there is a hell of an opportunity presented here, in terms of this technology, and nothing is written in stone. And there is this opportunity for us to, really make the best of what these new tools give us. And I think, as I remember, it was a few years ago now, but the Sunday Times, sorry, not the Sunday Times, the New York Times, did this fascinating article where it started with a whole series of quotes about how enhanced communication and information flowing was going to completely destabilize society and what have you. And then, of course, the denouement was that all of these quotes were taken from the 1900 at the time that the telegraph was becoming wide scale introduced in the flow of information, and yet they all looked as applicable today in terms of the way society was being upended, by social media and various other aspects. So I think we always have to understand that as rapid as progress appears to be today, it is every bit the same level of rapidity that people have felt previously. So for those of you that have participated so far, and those of you who intend to participate over the next 3 days, and in particular that I should emphasize, understanding these things, being able to use machine learning means that your level of debate, your level of discussion, your ability to see the best ways and apply this technology is really helped by having a proper low-level understanding. And therefore we are trying to get as much of an on-ramp for as many of you as you can to understand machine learning in all its various guises. We've picked 6 different example cases that we hope will provide an on-ramp to you. And then thank you again to our panelists. It's been absolutely tremendous talking with you. Hope to get a chance to see you in person. It was always fun. But thank you again so much for your contributions today. I think I don't know whether we can applaud on this system, but I will speak for all the audience as thanking you enormously for your very, very interesting discussion. Thank you.
Thank you,
Thanks,
Rick.
Richard, and
Really
thanks,
fun.
Ariel and
Thank you.
Lewis.